Hi, everybody. Welcome to the podcast Everyday Metallurgy. Today, we're going into space. Uh, we have never been here before because nobody has ever harvested metals or made any metallurgy in space. But my guest today is working on that subject. She started as a biologist looking for life in space, but after some years, she started to look for extreme life forms on Earth to see if they could be transformed into life form we could use to harvest metals when we go to live in space. This is the most crazy episode I have made so far, and I will really encourage you to follow through. At the end, Lynn is in fact inviting you to be a part of the project because she's very open-minded and she would like to share her findings with you. So keep on, stay to the end. It's wow, fantastic. Enjoy the episode.
Perfect. Hi, Lynn.
Hello, Peter. How are you?
Fine. Welcome to the podcast Everyday Metallurgy.
Thank you so much for having me.
Yeah. This is the first episode where we go off ground and talk about things in space because you're from NASA. Can you tell a little about yourself and what you do?
Yes, absolutely. I've been a civil servant at NASA my entire professional life, so getting close to 30 years now. And I was originally brought in to NASA as a biologist looking for life in the universe. So my
Hmm.
background's in evolutionary biology. Quickly got into life in extreme environments because, of course, if we're going to look for life elsewhere, we're starting to talk about environments that are extreme for planet Earth.
Mm.
And then about 15 or 20 years ago, I was asked to start a program in synthetic biology for NASA. And so a lot of my focus since then has been using biological tools to enable space exploration. And I think it's through that interest that we're here today.
It is, yeah. Because the theme is biomining in space, and biomining has been
Excellent.
going on ground for many years. Uh, can you give a short introduction to how biomining works and where it's used on Earth?
Exactly. So biomining is just it's a general term when people use life as a way to enable mining. And when people say biomining, most people are talking about bio-leaching.
Mm,
So organisms change the environment they're in. And there are organisms that do very well in ores. And so they may be producing acids that allow certain metals to leach out. And this is something that humans have taken advantage of, as you mentioned, for quite a while, I think
mm,
literally thousands of years.
yeah.
And this is still something that's being used around the world. I believe it's used in copper mining, for example.
Hmm.
But what we've done is something very different in biomining. So I've taken the actual definition using life biology to aid in mining. And instead of leaching, I've taken a totally different approach and started to think about what life is really good at. Now, what we're really good at is being very precise with binding metals, among other things.
Hmm.
So, for example, over 50% of the proteins in your body bind to metal. And then there are many other compounds in your body that bind metals. For example, hemoglobin binds iron.
Yeah.
And you need this. It's
Yeah.
not like you woke up this morning and your hemoglobin said, wouldn't it be fun to bind cobalt today or nickel or magnesium? It doesn't work that way.
Hmm.
Every hemoglobin molecule has to bind iron every day, all the time, or you're dead. Just like chlorophyll binds magnesium and
Yeah.
so on. And again, many
Yeah.
proteins bind various other metals. And so that's the kind of power of biology that I am trying to take advantage of. So I think, well, what if instead of using a whole organism to bind something, what if you just look at these specific biomolecules that are really good at binding a specific metal? And could you use that to make a filter to pull out that specific metal? And so we originally thought, well, there are certain biological parts that are exterior to the cells. So, for example, you think of a bacterium that has flagella so it can swim along. That flagella, these hair-like bit of the bacterium, are composed almost exclusively of just 2 different proteins or so. And so what if we engineered those proteins to bind a specific metal? So that's what we started off doing, and it worked really well. And of course, the next question is, that's great, and now you have metallic bacteria. So what do you do next? And that's where we were a little stuck. I mean, there are ideas, but they probably weren't economical. And then a few years ago, we started using a totally different approach. It turns out that fungal mycelia, the thread-like structures that most fungi have underground, if you've ever dug soil, you've seen these white hairs and so on.
Yeah, exactly.
This is the main part of the fungus, and then, so the fruiting body is a mushroom.
Yeah.
Well, it turns out we're using that approach to make habitats off planet, so making houses on the moon and Mars. So totally different project. But one of my students came in and said, I was reading that fungal mycelia can bind metals. And I know he kept talking, but I didn't listen to anything else he said. I thought, this is it. This is all the problem. What if instead of putting the proteins that we're talking about on the flagella bacteria, we put them on the outside of fungal mycelia? Because those are really easy to grow. They're cheap. We can grow them in any shape we want. We can easily have the metals released, anything we want. So now we have the potential for what I like to think of as a tunable filter for biomining. All we have to do is put a protein on that sticks to the fungus at one end and sticks to a metal at the other. And we've created a database now of, almost the entire periodic table of short sequences of proteins or other sorts of biomolecules that combined almost anything, again, on the periodic table, not everything, but much of the periodic table. And so we now have a system where you could pull out almost any metal you want. Now, I've been to some big mines, for example, in Nevada, and I know these are, I'm not stupid. I know these are very big operations. And to think that I'm going to replace some of the huge smelting operations is ridiculous. But there are aspects of this that are going to be far better than those approaches. So, for example, say you have effluent from a mine tailings, and you've got all sorts of waste particles, and this is bad for the environment, and you're losing metal that you might want. Well, this is already in an aqueous solution. This is a perfect time to use my approach to pull out these metals and be able to recover them on a filter, grow into any way you want. Or metal separation. As I said, your hemoglobin doesn't decide to bind a different metal one day. It's always the same all the time. So with that kind of specificity, we should be much better at separating metals, something that can be very difficult to do with other methods. And again, any metal, any conformation. So I'm really excited about this approach, as you can see.
Yeah, absolutely.
So that was a very long answer to.
Yeah, is it still alive, or is it only the molecules that you activate?
So that's a great question. There's no reason that the fungal part couldn't still be alive. We just don't want it to eat the molecules on the outside that are binding the metals, of course. There's no reason it can't be dead. I'm not even sure if we specifically killed the ones that we've used or just dried them and then used them. So that's a great question, but in principle, it shouldn't matter as long as the fungus itself is not digesting the binding metal molecules.
Because if you want to expand and you are off ground, then if it's alive, it can expand itself. But it also needs to harvest energy. And how do you harvest energy as a fungi here on Earth? Is it breathing
Well, that's a great thing. I
oxygen?
mean, yes, fungi breathe oxygen. And I mean, I'm saying and because the biologist in me says that that's not 100% true, because you can grow yeast anaerobically without oxygen. But the fungi
Mm.
we're talking about do need oxygen, you're right? But they literally eat garbage. I mean, again, go outside. Right now it's raining where we are. I was out walking around our woods yesterday. There are plenty of mushrooms popping up. The fungal mycelia are having a great time. And I'm not feeding them anything. They're finding plenty of organic matter out there. So
Yeah.
off planet, there's no reason they couldn't use human waste, or certainly agricultural waste. So, for example, you're eating maybe the peel of a cucumber or parts of a potato plant that you're not eating. Fungi will be more than happy to eat all that sort of thing.
Yeah. So
Actually, what we're doing for another project with the fungi is growing algae to try to feed them as well. But again, they literally will eat your garbage.
yeah. So if you're going to bring this into space, how will it work out there? Will you be able to grow it in space, or should you bring all the active molecules from the Earth and out?
Well, that's a great question, because that to me is one of the huge advantages of biological solutions, in that you don't need to bring it all from Earth. You bring a small amount, and as we all know, life is self-replicating. So as long as you bring a small amount and you have the material to feed it off planet, it can grow off planet. And so you solve what we call the upmass problem. It costs a lot to launch anything off the surface of the Earth. So if
Yeah.
you can bring just a little bit of, fungi that are able to do this and then grow it on the surface of a planet or an asteroid or the moon, you've
Yeah.
solved this upmass problem.
Yeah. And then if it needs oxygen, will you be able to generate the oxygen if you go somewhere else, or should you bring that?
Well, of course, we're going to need oxygen if we've got humans. You have no choice, because we breathe oxygen
Yeah.
as well.
Yeah. Yeah, of
Um,
course.
I personally, there are people using mechanical methods, but I personally like the tried and true method that planet Earth has been using for about 3.5 billion years, and that is taking advantage of photosynthetic organisms that take carbon dioxide. They photosynthesize, what they call fix the carbon dioxide into organic matter, and their waste product from the water is oxygen, and that's what we breathe. And I don't see any reason to reinvent that. It's worked really well for say, about 3.5 billion years on planet Earth.
Yeah.
And we're going to need the plants to eat anyway. So why
Yeah.
not take advantage of that?
Yeah. And the first microbes we had on Earth, as I remember it, the atmosphere, if we go back 3.5 billion years, was carbon dioxide. So the first microbes,
Correct.
they lived in that atmosphere and changed it to be as it is today. So if we go to Mars, Mars has an atmosphere that is almost pure carbon dioxide. Would you be able to reproduce that pattern going there?
That would be great if we do that. The only real problem is that Mars is smaller, and so it lost its tectonic activity and so on, and it lost most of its atmosphere. So you're right, it's about 90%, 95% carbon dioxide, but there's not much of it. It's it's a little less than 100th of the atmospheric density of planet Earth. So we're still probably going to have to concentrate. Yeah, the CO2. We've got what's called a bar pressure, 1 atmosphere, and it's only 7 millibars on the surface of Mars. So you're right. The composition's good, but there's not as much as we would like. It's sort of strange in this era to be talking about we don't have enough carbon dioxide because, of course, we're worried about it on planet Earth, but it's a totally different story on Mars when it would be nice to have it to convert to oxygen. It would be nice to have it to heat up the planet. But right now, there's just not enough in the atmosphere.
Okay. But if we were going to build a settlement and we brought these fungus with the protein that could guinea pig specific materials or specific alloys or metals, what kind of metals would you go for initially? Well, if we should build out a settlement, would it be iron to build houses as we do here, or or what kind of metals would we go for?
Well, that's also a great question. And I know which ones are easiest for me to do, the ones that life already uses. So, for example, things like iron and magnesium and copper and, all those are easy to bind.
Yeah.
Unfortunately, what people who are the engineers tell me is they want me to bind aluminum. Now, I don't know about you. I've never seen an aluminum organism.
Nope.
And so it's going to be trickier. However, I do know that they also need gold, and there are examples of proteins that bind gold. Think about the shielding, for example, for space helmets. There are plenty of other things that we do certainly need that are more amenable to biology. But I suppose if I have to make an aluminum binding protein, I suppose we'll have to do it.
Yeah.
So it's going to be the usual creative tension between the people in the space business who tell me what they want, and I say, I hope I can do that for you. With this, how about using some of these as well?
Yeah.
So it's going to be back and forth.
Yeah, and then next step is now the molecule has the if we are going for iron, but is it in ionic state, and how is it water solvable, and do you go hydro metallurgy to make it into the metal form? So how do you get it out again?
So no, right. So what we've done is just had this in solution, and I guess the form is going to depend upon the pH, and that's going to affect the protein. So you need to find a happy medium depending on what the metal is and what the protein is. I forget what we used for copper, but it all worked very well with the copper and the zinc and so on that we tried. How do you get it back off? So as I was alluding to, it's going to depend a little bit on the pH. And the acidity, the basic environment is going to depend, it's going to affect how the protein folds. And so that's a really common way when you use proteins to bind things to get them released is by changing the pH. To either make it more acidic or less acidic. But again, that's different than an entire metallurgy factory. All you're doing is now talking about this little filter that has your bound metals to be able to release them and then start again.
Yeah. So the protein could be in basidic state, open, and then when you have acid, it closes around the iron metal. So you can make it open and close and reuse it again?
Yeah, I mean, that's the basic idea. Yes.
Yeah.
I mean, of course, since the fungus is just organic material, you could also, in principle, incinerate the whole thing and just be left with the metals. So you get rid of all the organic material that your filter is made out of and just have the metals left. I mean, there's certainly other ways to do it as well.
So then when you have the metal, you still need some pyrometallurgy, or is it in metallic state at that time? Can you press it, powder metallurgy, or and sinter it, or do you need to make some chemical reduction to it?
So I haven't really gotten into that part of the processing. All I'm doing is focusing on the recovery, separation, and release it, and then someone else is going to worry about the downstream. And of course, it's going to depend what they need it for.
Yeah.
So what I could do is, in principle, have a very pure fungus that has just bound gold or whatever, and then I can release the gold, and so you've got a solution of gold, and then say, go take it and do what you need to do with it.
Okay.
So what I'm trying to do is, you can see, is create a system that's really flexible, because particularly when you're off planet, you can't take 135 different systems with you just in case you might need one. And to me, the beauty of this system is all you have to do is change a protein, and then you change what metal you're binding. I probably should have mentioned that there are people who also do biomining with organisms that naturally bind or concentrate metals, and there are few of those, and that's great. There are few organisms that already will form metal inner particles, for example, magnetite crystals. There are few organisms that will make magnetite, but that's, again, great if that happens to be the particular metal and the particular form you need. And to me, life is too short. I want to be able to solve all the problems at once. And so that's why I've been focusing on a tunable filter.
Yeah. And how do you test this in the lab? Can you give us some insight in how such a lab looks like?
Certainly. So I have a reasonably large lab at NASA Ames, and we're set up to do microbiology and some field work, some work on extremophiles, and then a lot of synthetic biology. So it looks pretty much like a biology lab would look in a molecular or a bioengineering department. And the way we've been testing it is to make specific solutions of the metals and mixed solutions, and then make little prototype of these fungi with the bound proteins, and then flow through or have them sit in the solution and pull it out, and being able and testing how much is bound and how much is left in solution, and then releasing and finding out how much you've released, that kind of thing at a small scale. So we haven't done anything industrial or commercial. I'm a civil servant. I work for the US government, so I don't form companies or anything else. But one of the graduate students started with this work originally with me, did form a company, and I know was pursuing it at one point. And we're certainly hoping that many other companies take our IP, our intellectual property, and run with it. Because again, I can't do that as a government employee, but what I love doing is coming up with the great ideas, and hopefully other people will take these ideas and, again, commercialize them and run with them.
Yeah. Yeah, I like that idea of being able to separate every single metal. I know that in copper mining, microbes are used, and typically when you go copper refining with melting technology, you have a lot of arsenic going with it. So the arsenic is very poisonous, and when you melt it, it evaporates, and it condensates in the surrounding area, and makes that totally dead for life for many years. But if you go biomining, the biological microbes only want the copper, so it leaves the arsenic in the leftovers. So it's a way to extract exactly what you want, and that's pretty much what you say. But if you can do it on all kind of metals, then it can be a game changer in the long tail in a typical mine as well.
Oh, absolutely. So there's no reason to leave the arsenic. Why not find that as well? Have a second filter. And one filter is used for post-processing, the other is to just clean up the mess.
Yeah,
so you're using it for extraction, bioremediation all at once.
Yeah. So if we bring this with us to Mars, there are a lot of precautions when you make a satellite and you go out, because we don't want to bring life form and pollute when we send out satellites today. But what will happen if we bring this kind of life form? Will it change the planet forever, or what do you see?
So, as I mentioned at the beginning, my background is in evolutionary biology. I was brought into NASA to look for life in the universe. And so, wearing my other hat, that would be a tragedy if we polluted Mars with organisms and didn't have the opportunity to see if there was already life there. So, of course, I'm very well aware of that. But there are multiple ways we can go about doing this. But the bottom line is that once we have humans there, human life is going to take priority. And so what we really want to do is do as much of our searching as possible first, so that when we do have humans there and there's a problem and we vent microbes out into the environment, we've already done most of our searching and it doesn't become a question of one versus the other. So I think that that's critical, that we have these robot missions in advance. However, that being said, we should be able to determine what is the particular organism that we put there. The chance of a Martian organism evolving to be identical to the fungus that we're bringing is basically zero. Because you think of all the twists and turns of evolution, even if life started the same 3.5 billion years ago, and there is an argument that life could have started on Mars and come to the Earth. So even if it started with the same building blocks, the chance that there would even be a Martian fungus, much less identical to the one we're bringing, is almost zero. Now, there are other sorts of things that you can do to watermark organisms. You could put in a little sequence of DNA that says, for sure, this is something I brought, so I know it's mine. The chance of
You can
this
mark
evolving naturally.
Yeah.
Yeah, why not watermark it? And that's been done before, putting in, sections of DNA that you know are there because you put them there, and nothing else is ever likely to have. So that there are things like that we can do with it. Now, if you're worried about it taking over, fungi, as we said at the beginning, need organic material to eat. And there's been very, very little found on Mars so far. It's been vanishingly small, and it's been mostly in a gas form. And so, honestly, between the temperature, the fact that liquid water is not stable, the radiation regime, and there's nothing to eat, I'm not terribly worried about my fungi getting out there and taking over Mars. They could fly around in a dried form that could potentially be reactivated someday, but with the radiation, chances are, if it were near the surface for not too long, it would be killed anyway. So I'm not tremendously concerned about that, but obviously we have to think this through, and we don't just go and throw fungi out in the surface without being very much well aware of planetary protection protocols.
Yeah, and
I hope that
the
helped.
radiation might also make some changes of the DNA in a more rapid pace than we see here on Earth. Don't you think?
Well, yes, but the thing is, I think it's going to be so much, unless it's covered by Martian dust or whatever, that it's going to be dead. It's not a matter of a few mutations. It's a matter of so many that it's going to be killed. If you're under a rock or something, you might be able to survive. But then, even if there are a few mutations that are in principle hazardous or whatever, if there's no liquid water, they're not going to grow. Nothing's going to happen. They're just going to be some mutated dried bits of fungi out there.
Yeah, wonderful. I have a few questions left. One is, if we already talked a little about it, spin-off potential, because many NASA projects has shown spin-off a lot of investment in developing the big solution to go into space, but it is used in our everyday life here on Earth. And the podcast is called Everyday Metallurgy because I would like to relate to our everyday life. So do you see a potential in bringing this new technology out into our everyday life?
Oh, absolutely. And again, I preface this by saying I'm not in the business world, so I don't know the economics of it and so on. But I can't imagine a method that you can grow on something that has virtually no cost. You can grow on agricultural waste, and tune wouldn't be economically advantageous. Now, the advantage I have for space is that there's no existing industry. So there's not already a metallurgy industry on the moon or Mars, and so
Mm.
I can start from scratch.
Yeah.
Unfortunately, or fortunately, there is on the Earth. So I know that obviously there's already investment in manufacturing, extraction, remediation, and so on. So my
Mm.
ideas would have to displace what's already in operation.
Mm.
However, I think because of the specificity, so it actually does better than current technologies, and it's much greener, it's much more environmentally friendly. I can't believe it isn't also ultimately cheaper for some
Mm.
things. Again, I'm not going to claim that you should shut down all mining operations and my fungi will take care of it all. But
No.
I think particularly when you have an aqueous stream, you have the acid mine drainage that needs bioremediation. This is perfect for that.
Yeah.
Anytime you already have a liquid solution. But we originally got into this because we were also very interested in recycling urban urban waste, e-waste.
Yeah.
And so what we're talking about are things like, computers and cell phones. And so what I always say is if you wanted to build a cell phone on Mars, the best place to get the components of the cell phone is from a dead cell phone. So why not
Hmm.
grind up your one that no longer works, pull out the metals and make a new one? Why go all over the planet when the metals are
Yeah.
right there, exactly
Mm.
what you need? It's a matter of pulling
Yeah.
them out, making a new one. And
Mm.
maybe, the case is fine, but you need to pull out metals from the integrated circuit, which was exactly how we originally got this project funded, by
Mm.
saying that we could make a recycled integrated circuit. Ground it up, pulled out the copper, and we're able to reprint an interconnect.
Yeah.
So that's exactly the sort of thing that we got interested in. And obviously, e-waste on the Earth is a huge problem. And I do think that
Mm.
this is one of the solutions for that as well.
Great idea. I could also see a potential. I have a good friend that works in cleaning polluted dirt for heavy metals. And this could
Perfect.
be
I
a
mean,
way
not
of,
perfect for him, but
yeah, but this could be a way of, if it's polluted with the lead, these microbes could it could pick out the lead and clean the dirt.
absolutely. Absolutely. Yeah, I'd love to
Fantastic.
hear more about that. That sounds like perfect application.
Yeah.
I should add, and maybe your viewers know this, there are some people who also do phytomining. So there's some plants that bind metals on their roots, for example. And so that's an interesting thought. I know that there's been some work with heavy metals in that area as well.
Hmm.
What a brilliant idea if you could plant some of these plants along roads where the heavy metals are being
Yeah,
deposited from
exactly.
trucks and so on, and being
Yeah.
able to pull them back out. But again, in that situation, they've already evolved for certain metals. I think that it's a perfect system. Use it when it's appropriate. It's a little different than mine, but you don't need one solution to all the problems.
Mm.
You have multiple solutions.
Yeah, exactly. Wow. I am more than filled up in my head now. Uh, if I would like to learn more about this topic, where could I go? Where could I find more information?
Great. Well, we have one paper out on this so far, and that was published in Scientific Reports a few years ago. The first author on that is my graduate student at the time, Jessica Urbina. Um, I can find the year for you, but my guess is it was maybe 2019, somewhere in there. I can look that up for you quickly. And we just had a US patent issued that has much of this information as well, and that was based on the paper.
Fantastic. I'll share the paper in the comments in the YouTube channel, so people can go view it there.
Thank you. Great. I just confirmed it. It was published in 2019, and Jessica Urbina, Urbina, was the lead author on that. But that came out of my lab.
Wonderful. Thank you very much.
And I would encourage people. Yeah, I would encourage people who are interested, and certainly people who are interested in leasing the patent. We are very interested in having that used because, again, I can't say it enough. I can't take it and run with it, but that's the whole point of patenting these things, is hoping that other people do have a use for it. And I hope some of your listeners do, and they let me know.
Yeah. It is one of the purpose of this platform to share information and lift up each other. So I'm sure that if somebody are interested, they'll reach out to you.
Terrific. Thank you so much, Peter.
Thank you very much for joining in.
Thank you very much for listening and following this podcast. If you have learned as much as I have, you are pretty clever today, because I had never thought of changing the genome of mycelia to be able to harvest specific metals, as Lynn just explained. It looks as a fantasy story, but I believe it's possible. It was very interesting, and I will encourage you to follow up, read her paper, look at her patent, reach out to her if you are a miner and you want to use this or test it in your facility. It could be to separate specific materials you don't want out, or it could be to pick out exactly those metals that you want. That is what her technology can do. So thank you very much for following. And if you like this episode, I will be so happy if you will share it, if you would like it, if you will comment on it. And of course, if you will follow the podcast as subscriber on YouTube. Thank you.